Why do we need relativity in particle physics? Of course, one can describe the state of an electron in the hydrogen atom without invoking relativity. Note that this does not mean that relativity does not play any role in atomic structure. After all, gold is yellow and mercury is liquid due to relativistic effects. But the reason for using relativity in particle physics is that most reactions which are used to produce new particles occur at so high energies that relativistic effects cannot be neglected. In fact, we often have to consider the ultra-relativistic limit with velocity v close to c, where c is the speed of light. For instance, massless particles such as photons travel at v equals c. Extremely light particles such as neutrinos are also always observed moving at a velocity very close to c. But why do we have to consider relativity in processes involving particles with finite masses? Take the example of the reaction electron plus positron gives muon plus antimuon. We will discuss the nature and the properties of these particles later. For the moment, it is sufficient to know their masses. Mass of the electron is equal to the mass of the positron, and that's 0.511 mega electron volt per c squared. And the mass of the muon is equal to the mass of the antimuon, and that's 105.658 MeV per c squared. Using the conservation of energy, we have where K denotes the kinetic energy of the particle. Even if the muon and antimuon are produced at rest, we see that the sum of the kinetic energies of the electron and of the positron is as the mass of the muon is much larger than the mass of the electron. This implies that the electron and positron are ultra-relativistic. Indeed, their kinetic energy K is orders of magnitude greater than their mass energy mc squared. This is often the case due to the large difference of masses between particles.